In this video, we'll have a look at the type of transformations that can occur to the graph of y equals x squared. We hope it can be useful for you. To check out other mathematics videos and to support us, please subscribe to our channel. Let's first of all have a look at the graph of y equals x squared, and we'll do that via a table and then plotting the points on the graph itself. Our axes in this picture go from -3 to 3 on the x-axis and from -2 to 18 on the y-axis. So we'll start at -3 and we'll plot the x values going from -3 up to 3, 1 unit at a time. So because this is x squared, we're multiplying the x values by themselves, in this case -3 by -3. Two negatives make a positive and 3 3s are 9. So our first value is 9. We'll plot that point there matching -3 and 9. And then we'll go back to the table and do -2 by -2, which is +4. So at x equals -2, the y value is 4. Following on from there, -1 by -1 is +1. Again, we'll plot that point at -1, 1. 0 squared is just 0. One multiplied by 1, or 1 squared, is equal to 1. And we'll see here we've got a mirror image of what occurs on the left of the y-axis all the way through to x equals 3. So at x equals 3, its y value is 9. Joining those points together in a parabola shape, we now have our curve which matches y equals x squared. And we can see that we've got a turning point at 0, 0, or the origin. Let's have a look at our first transformation to the graph y equals x squared. And we'll look at the equation y equals x squared plus 2. We've set up our table so we've got our x values in the first row, the y values which match y equals x squared, and in the third row of our table we've got the y values which match x squared plus 2. So when x is equal to -3, we square that, and we saw beforehand that equals 9. And then we add 2. So that means that 9 plus 2 will give a value of 11. So that's our first y value matching the equation y equals x squared plus 2. And in fact, all we're going to do is add 2 to all of those values that we had previously for y equals x squared. So we'll plot those points from the table on our graph, starting at -3 for x and y equals 11. And then proceed through the other values given in the table all the way through to the point 3, 11. When we join those points for y equals x squared plus 2, we can see here in our new graph that the parabola is the same shape. So in other words, it's congruent to the original graph, but it's just been moved 2 units vertically. So we say the transformation there is a movement of 2 units vertically parallel to the y-axis. Here's another example where this time it's not +2 but it's -2 after the x squared. So if an equation is written in the form of y equals x squared plus or minus a value, what we can see is a vertical movement of the graph. In this case, the parabola has moved down 2 units, again parallel to the y-axis. And we can see that the turning point is no longer 0, 0, but for the new graph, it's at 0, -2. So to summarise that, we can say that if you've got a graph of y equals x squared plus q, where q is some real number, then the graph of y equals x squared moves vertically upwards parallel to the y-axis q units. We say parallel to the y-axis to indicate that it is straight up. In other words, matching the same direction as the y-axis. Let's have a look at what happens when the equation is written in the form of a bracket of x minus or plus some value all squared. In this case, it's x minus 1 squared. So what we're going to do is first of all subtract 1 from -3 to get -4. And if we square that, we know a negative multiplied by a negative is positive, and 4 4s are 16. So when x equals -3, y in the case of x minus 1 all squared is equal to 16. Now let's go to the x value of 2. 2 minus 1 is equal to 1, And if we then square that, we get 1 multiplied by 1 is 1. Let's now try another x value. We'll go in the middle of the table and do 0. So 0 minus 1 is equal to negative 1. And negative 1 squared, so two negatives will multiply to a positive, and 1 multiplied by 1 is just 1. Going in between those last two x values, we have that 1 minus 1 is 0. Of course, when you square that, you get 0. At x equals 3, if we take 1, we get 2, and 2 2s are 4. It appears as though the table is moved 1 unit to the right. So those two missing values logically will be 4 and 9, but you can check those for yourself. So now let's plot the points from the table, starting at x equals negative 3 and y equals 16. Plotting those points then leads us to the final graph for y equals x minus 1 all squared. We can see here that compared to the original parabola of y equals x squared, the graph for y equals x minus 1 all squared appears to have moved 1 unit to the right. So it's a movement parallel to the x-axis. So the movement of the points appears evident here when we look at the original y equals x squared graph to the new points for y equals x minus 1 in brackets all squared. So even though there's a minus 1 in the bracket, we see a movement of 1 unit in the positive direction, in other words, to the right. So what happens if we change our equation? So instead of being x minus 1 in the bracket all squared, what if we change it to x plus 2? We can see here in this next picture that if we were to go through and graph the points for y equals x plus 2 all squared, we have a movement horizontally 2 units to the left. So a summary for this is that if we have an equation expressed as x minus p all squared, the change to the original graph, in other words y equals x squared, is that the movement has occurred horizontally, and to be specific, parallel to the x-axis, and it's occurred to the number of units expressed in the bracket, except that in the case of minus p, it's moved p units to the right, in other words to the positive direction. Let's have a look at what happens when we make two changes to the equation for y equals x squared. So in this case, what we've got is x minus 1 all squared in the bracket and a plus 2. Let's try putting x equals negative 3 into that equation. Negative 3 minus 1 is equal to negative 4. If we square that, a negative multiplied by a negative is positive, in this case positive 16. And then we're going to add 2, and 16 plus 2 gives us 18. So going through the table, if we look at the next value, we've got negative 2. If we take 1, it becomes negative 3. Square it, becomes 9, and add 2 to get 11. Quickly going through the rest of the table, at x equals negative 1, we have a y value of 6, and then we continue to have y values of 3, then 2 at x equals 1. At x equals 2, it's 3, and at x equals 3, the y value is 6. We can plot those points on the table quite quickly as we did beforehand. So we can see a parabola taking shape here, but what's of significance is that point, which is the turning point or lowest point on the graph, is the point 1, 2. And that ties in with the equation y equals x minus 1 all squared plus 2. Let's have a look at the final form of that parabola. According to our rules that we saw earlier, the minus 1 in the bracket indicates a movement of the graph 1 unit horizontally, and the plus 2 outside the squared bracket indicates a movement vertically. And we can see that here on the graph. If we look at each of the points on the original graph and then tie them in with the new points, we can see that we've got a horizontal movement of 1 unit to the right, and we've got a vertical movement 2 units upwards. And that's the case for each of the points on the original graph. We can go 1 unit to the right and 2 units up, and we'll find a matching point on our new graph. Now let's explore another change to the equation for y equals x squared. This time we'll multiply it by putting a 2 out the front of the x squared, which of course in order of operations we need to square x first and then multiply it by 2 because indices comes before multiplication. So each of the y values represented in red, which is x squared, can be multiplied by 2. And we can see in the table that each of these values is basically doubled. So once the table is completed, we'll go ahead and plot these points on our graph. Now it's interesting to note the change that's occurred. Let's have a look at x equals -1. The y value for the point has increased by a factor of 2. Likewise, when x equals -2, it's been multiplied by 2. So previously y was equal to 4, now y is equal to 8. So the greater the y value, the greater the change that we can see. And when we have a look at our completed graph for y equals 2x squared, we can see that the parabola has become narrower or steeper. So we call this a scale change or a dilation, where that scale change is parallel to the y-axis. In other words, the movement occurs vertically in terms of each of the y values being increased by a factor of 2. If we change our equation by multiplying x squared by a negative, in this case simply multiplying it by -1, we find that the parabola for y equals x squared is reflected about the x-axis. So let's have a look at the changes that occur when we multiply x squared by some value. So if we multiply x squared by a factor a, where a is positive and greater than 1, what we see is a parabola that becomes narrower or steeper because all of the y values are changing by that factor a. Now if a is a fraction less than 1, for example a half or a quarter, and it's still positive, what happens is the graph becomes flatter or wider because all of the y values now are decreased. So for example, if a is a half, the y values are half as much as they were before. If a happens to be negative, we see the same changes as if a was positive, but the parabola is reflected about the x-axis. So in effect, it's upside down compared to what it was originally. Let's have a look at what happens when we multiply x by some value prior to squaring it. So in this case, we'll have a look at y equals, in brackets, 3x all squared. So let's complete our table again. We'll start at -3 for x, and if we multiply that by 3, we get -9. Then once we've got that, we'll square it. So we get -9 squared is equal to 81. Repeating the same process, we can quickly fill in the rest of the table for the other x values from -2 onwards. So unfortunately we can't plot at x equals -2 and -3, but we can plot at x equals -1, 0 and 1 as it's still within the range of the values on the y-axis. So in considering the change of our original parabola y equals x squared to the new one for y equals 3x all squared, we'll consider it from the perspective of horizontal change, simply because we're multiplying the x by 3 prior to squaring. In other words, it's a change with the x values. Let's start by looking at x equals -3 on our original graph of y equals x squared. We can see horizontally that that point has contracted towards the y-axis or parallel to the x-axis by dividing by 3 or a factor of 1/3. Likewise on the right-hand side. So this is purely considering it from the point of view of horizontal change. So we can see here the final version of our graph y equals 3x all squared. The way to think of the transformation is the original graph of y equals x squared is contracted by a factor of 1/3 towards the y-axis or parallel to the x-axis. Let's have a look at a half x squared. In the first case, we'll take a half of -3, which is -1.5, and then when we square that, we're going to end up with a positive result, and it's equal to 2.25. So what we'll do in each case is we'll halve the x value and then square it. So a half of -2 is -1. When squared, that's just 1. A half of -1 is -1/2. And when we square that, we get +1/4 or 0.25. A half of 0 is just 0, so that's easy to square. The rest of the table will then give y values, which are a mirror image of what we saw for negative values of x. If we then plot the points from our table onto the graph, what we'll notice is we seem to be getting a parabola shape that's being stretched out horizontally. Let's have a look at the final graph to see what effect our half in the bracket has. We can see here that the parabola has been stretched by a factor 2 horizontally. In other words, all of the values of the original parabola for y equals x squared have been stretched out parallel to the x-axis, so they're now twice as far away from the y-axis. If we go back to the points we plotted, we can see here that each of the values on the original y equals x squared graph can be stretched out by a factor of 2 horizontally to go to the new points that we've achieved for the graph y equals a half x squared. In other words, every point on the original parabola is now twice as far from the y-axis because it's been stretched out horizontally. So we can put this transformation into a rule. If our original function y equals x squared is modified by multiplying the x by some factor b prior to being squared, then what we see is a dilation parallel to the x-axis, or in simple terms, the graph is being stretched or contracted horizontally, and that factor is by 1 over b. So we saw in the previous example when b was equal to a half, the factor would be 1 over a half, which is 2. In other words, everything is stretched out horizontally by a factor of 2. Let's have a look at what happens when we combine some of these changes into one rule. In this equation, we're seeing 3 modifications to y equals x squared. We're introducing brackets where there's a minus 1 prior to squaring. Then we're multiplying that squared result by 2, and then we're adding 2. So working from the brackets and then working outwards, what we can see is the minus 1 inside the bracket next to the x is going to cause a horizontal shift. The y equals x squared graph will move 1 unit to the right. Then multiplying that squared result by 2 will create a scale change vertically. Everything stretches out by a factor of 2. And then the plus 2 at the end means we move that resulting graph up 2 units. What's interesting to see from the graph and also the equation given is that our new turning point is the point 1, 2. Let's have a look at an equation where the resulting graph may not be so obvious. So in this case, we've got y equals, in brackets, 2x minus 1 all squared plus 2. Here's our resulting graph, and it might be wise to pause here and see if you can come up with an idea as to why you think this graph is positioned and shaped like it is before we actually go through the steps as to how we resolve this. When considering changes to the original graph of y equals x squared, it's advised that any factor of x is factorised outside of the bracket squared before we start. So in this instance, we're going to factorise the 2 outside of the 2x minus 1. That will be left with 2, and then in the square brackets, x minus a half. And that whole expression, the 2 and the square brackets, is still going to be squared, hence the other pair of brackets. And then we've got the plus 2 at the end. The next thing we'll do is we'll square the result. So 2 squared is 4, and we'll leave the enclosed bracket x minus a half all squared as is. So now we can identify the changes in a much simpler manner. This might be a good opportunity to pause and see if you can work through the transformations for yourself before we go through and reveal each of the steps in a moment. As before, let's work inside the brackets. So the first transformation, because there's a minus a half, indicates that the graph has moved half a unit right parallel to the x-axis. The next change we can see is that there's a 4 outside of the bracket squared. This is going to create a vertical dilation by a factor of 4, in other words, parallel to the y-axis. And the last change we can see is the plus 2 at the end of our equation. This will indicate a vertical translation, in other words, everything on the graph moves up 2 units parallel to the y-axis. So what we should see in our final graph should be a narrower graph or steeper graph compared to y equals x squared, and the turning point for the graph will have the coordinates a half and 2. So we can see in our final picture here of our graph that there is a narrower parabola compared to the original y equals x squared. It has moved to the right and moved vertically up, and we can tell that clearly from the turning point, which was at 0, 0, and now is at the point a half 2. Let's have a look at a transformation for the point 0, 0 on y equals x squared. And we'll start with a minus a half in the bracket, which indicates a horizontal movement from 0, 0 to the new coordinates of a half 0. Now the next change in the transformation is a scale change of factor 4 vertically. But if y equals 0, that's no change at all. And lastly, we have a change by adding 2 units. So the coordinates are now a half 2. So what we've identified there is the new turning point for the new equation, and that's the coordinates a half 2, based on the starting coordinates of 0, 0. Let's have a look at another original point. In this case, we'll go with the coordinates negative 2, 4. Our first change is a horizontal movement half a unit. So we get negative 1.5, 4. We now have a scale change of a factor 4 vertically. So our y coordinate changes from a value of 4 to 16. The x coordinate is still unchanged at negative 1.5. The last change we see is plus 2. So that means that our y coordinate moves vertically 2 units, and our point now has the coordinates negative 1.5, 18. Now we perform that transformation by looking at the original equation, which we can see at the top here, and taking the coefficient of x, in this case 2, and removing it outside the bracket, ultimately squaring it to get 4. Do we have to apply this process all the time? Well, no, we don't. We can also do a transformation of the original form of the equation as follows. In the first instance, we'll have a look at the original 2 next to the x and say that means that we have a horizontal dilation. Now the factor is going to be 1 over 2. In other words, the graph is contracted horizontally. The next step is to notice the negative 1 inside the bracket. Now that would indicate a movement to the right, but it's not a movement by 1 unit. It's a movement by 1 over 2. And the reason why it's 1 over 2 is because we have to acknowledge the factor in front of the x. So in this case, that a half, or 0.5, was calculated by going 1 divided by 2. And the last step is, as before, we see that we have a vertical movement parallel to the y-axis by 2 units, which is indicated by the plus 2 outside of the bracket squared. If you perform all of those steps to the graph of y equals x squared, you'll end up with the same graph that we did in our last example.